Hello. So I'm gonna continue with this thing here, right? Differential equations. Describe the orthogonal trajectories for the family of curves given by y equals c divided by x. Now, what does that mean? It means that this is a family of curves. What is that? Well, it's gonna be like x, y is equal to c. So if you say that c is equal to 5, all the family of curves that make c equal to 5 are part of the same family. Okay, all the curves that make c equal 5 is part of the same family. All right, so you want the family of curves that are orthogonal to the trajectory of this family of curves. You want the family of curves that are orthogonal to the trajectories of this family of curves. So what is orthogonal? Orthogonal, the derivative, is going to be the negative reciprocal of the other one. Okay, so if I say that, for example, I have a line M in here, and I have a line N like this, which is orthogonal. Okay, I can say that the slope of M, I can say like M and the slope, okay, is orthogonal to the slope of N. So if M, let's just say that M is equal to 2, the slope of N is going to be the negative reciprocal, which is minus 1 minus half. Okay? So here's the thing. You got to find out y complement, right? You got to differentiate this with respect to x. We could do this a certain way, but you can also do it another way, like y is a function of x. So this is going to be the product rule. So this is going to be the derivative of the first one times the second one plus the first one times the derivative of the second one, right? So it's derivative of the first times the second plus the derivative of the second times the first equals 0, because I'm differentiating this with respect to x, and I'm also differentiating this with respect to x. So what does that mean? You have y complement equals minus y divided by x. Okay. The minus y over there divided by x. Okay. So now I'm going to separate the variables. So the minus y comes over here. Actually, I'm just going to keep the minus here. I'm going to derive this by y. I put the y over here. Okay, that's what I did. And this is dy dx. Okay, this right here is dy dx. So I'm going to erase this thing. I'll leave the dy in here, and the dx, I'm going to multiply it over here, like that. Now all you have to do is integrate, right? It's going to be the ln of y equals the minus, I'm taking the negative out, ln of x plus c, right? Well, in fact, you didn't even have to do that. I'm trying to solve this thing, but you didn't even have to do that. All you gotta do is like, hold on, let me just go back a few steps in here. There. Okay, so now we found this thing. This thing is the derivative of this family of curves in here. It's gonna be minus y divided by x. So the negative reciprocal, okay, the negative reciprocal is going to be y complement equals x over y. And now we have to find the family of curves that has this stuff. Okay, so to do that, I'm going to say y complement y equals x. This means dy over dx times y equals x. So y dy equals x dx, and then integrating this stuff, okay, you have y squared divided by 2 equals x squared divided by 2 plus c, right? And now I'm going to multiply everything by 2. So it's going to be y squared, and I'm going to bring this thing over to this side, okay? Minus x squared equals c, and you go like, oh, hold on. I'm also multiplying the c by 2, right? Yes, I am. But what is 2 times a constant? It's another constant, so it doesn't matter what the constant is. Just write c. This c is not this one. If you want to make absolutely clear, you can see that this is c1, and 2 times c1 is c2, but it doesn't matter, because once you get to the end, all you gotta know is that this is a constant, so it becomes a c anyway. So that's it, guys. So what does that mean? It means that this family of curves, for every for the x and y point, is gonna be orthogonal to this family of curves for the x and y point. Okay. Now we're gonna talk about growth of a population proportional to a constant when there's a limit. Okay, I'm gonna say that y, for example, dy dt, which is the growth of a population, or decay of a population, is gonna be proportional to the size of the population. So you know that you have a ky in here, but it's not enough because now we have a limit. So we add this thing here, 1 minus y divided by L. The L is the limit, okay? Now let's just say that you have just a 1 in here, y is equal to 1, you have, or maybe 2, right? I mean, you have 2 to make them breed. So what is going to be the growth if y is equal to 2? So it's going to be k times 2 times 1 minus 2 divided by L. Now let's just say that L is very large. The limit for the environment is like 1 billion, okay? You just have 2 individuals, but you can have up to 1 billion individuals. The environment can have sustainable growth up to 1 billion. So since this is 1 billion, this thing is going to be very close to 0, okay? So this approaches 0. As that approaches 0, you know that this whole thing is just going to approach 1, okay? And the growth is going to be proportional to the size of y, which in this case is 2. But anyway, the growth is going to be proportional kinda to the size of y. Okay, now let's think of something else. Let's just say that y is getting close to the limit. If it's getting close to the limit, this thing here is gonna approach 1. Okay, I'm gonna have to undo it. So you got a value of y here, whatever it is, and then you have 1 minus y divided by L. Okay, and this y is approaching the limit. So this is approaching 1. As this approaches 1, this whole thing approaches 0. So what is gonna be the size of the growth or decay? Is going to be close to 0. Okay? Why? Because if the population is already reaching that 1 billionth limit, the growth is going to be very small. Okay? You already have 999,999,999 or 998. It's getting close to that 1 billion. So the growth of the population is going to be very small. Okay, now the thing, there's something else that it's going to be necessary. Well, I'll do it as we go along, okay? So let's integrate this stuff so we can find the solution for this. So the dt is going to come over here, okay? dt comes over here. We're separating the variables, and this comes over here. I'm gonna put this stuff a little bit further. This thing here, I'm gonna get it up. I'm gonna divide this thing here, okay? And the equal, I'm gonna put it here. The k, I'm gonna put it here. And forget about this, forget about this. The dt, I'm gonna put it here. Okay. Now here's the thing. How are you gonna integrate this stuff? Because you want to integrate it, right? Well, let's see what's going on in here. The dy, I'm gonna put it over here, and this thing here, I'm gonna turn it into a 1 to make it clearer. So what do you have in here? Let's multiply this out. Okay. So let's multiply this out. What is this going to be like? This whole thing in here. Okay. You have 1 divided by y minus y squared divided by L. Doing this, I can put an L here, okay? And then I can put this L that's down here over here. So I'm going to put the L here, and I'm going to erase this thing here. Okay. And this is going to be equal to L divided by y, right? I'm factoring out the y. So you have L minus y. L minus y. Okay. So this equals this. Does that help us? Not yet. Not yet. Because you still have a y in here and you got an L minus y in here. How are you going to integrate that stuff? It would be a lot simpler if you could just separate these two. Okay? Instead of expressing this whole thing as one fraction, I'm going to make 2 fractions. So I'm going to say this equals, all right, 1 fraction plus another fraction. One of the denominators of the fraction that I want is going to be y, because I want this y here. Okay? Now, I need to find what the other denominator is going to be. But I have one piece of information missing here, another piece of information missing here, and another piece of information missing here. I don't want that. So I'm going to force, I'm saying this is equal. This is equal to this. Okay, this is by force. So I'm going to force the numerators to be 1 and 1. Can I do that? Yes. All I got to do is to find the right denominator here that's going to make this thing become equal to this thing. So here's what I'm going to do. I'm going to say that this is A. All right. And now this is going to be equal to what? Well, let's continue over here. I'm going to unite these two fractions here. So the minimum common denominator is going to be AY. So AY divided by Y, A times 1A, plus AY divided by A, Y times 1Y. Okay, and I want this A plus Y in here, I want it to be equal to L. So I want A, because this is the numerator after these. You see what I'm doing? You have these functions that are united here, and they're also united here, right? So I want A plus Y to be equal to L. What is A gonna be? A equals L minus Y. There you go. Now I know what to do. I'm gonna put in A minus Y in here. And L minus Y, L minus Y. And there you go. Okay? No, hold on. Yeah, that's what it is. Because this is supposed, hold on. Yeah, L minus Y, yeah. Because it wasn't supposed to work so well like this. I'm factoring out let me see here. Yeah, it wasn't supposed to work perfectly like this. I think that I made a mistake. Hold on. This happens, guys. This happens. So y times 1 minus y divided by L. Okay, so the whole thing is going to be y minus y squared divided by L. I can put an L here, and then I can write extend. Okay, so 1 divided by this, I'm going to put an L divided by L y minus y squared. Factoring out the y, you got an L minus y, and it just worked. Yeah, in this case it just worked. But anyway, L minus y, because you see this y came over here and L minus y came over here, but this is not always the case. Okay, sometimes things just don't work this neatly. Anyway, this time it worked. Okay, so over here, what I'm gonna do is to say, hold on, let me just erase this in here. I'm gonna erase this here. I'm gonna say that on this part, okay, this whole thing is gonna be equal to this. So this is 1 over y plus 1 divided by L minus y dy equals to k dt. Okay, so anyway, now it's easy to do this, right? It's going to be the ln of y plus the ln of L minus y. Actually ln of y, and then L minus y divided by the derivative of the inner function with respect to y, which is minus 1. So this is going to be a minus in here, like that. Okay, equals k, which is just a constant, integrate with respect to t, which is just going to be a t plus c. Okay, now what do you have in here? In here, because of this minus, you can say that you have ln of y divided by L minus y, and this thing here equals kt plus c. Now continuing over here, it's going to be e elevated to this, which is equal to that, but e elevated to anything is positive, so I can guarantee that this is going to be positive. So I can get rid of the absolute value operator. Y divided by L minus y is going to be equal to e to the kt, all right, e to the kt, yeah, e to the, hold on, yeah, well, to leave the limit in the numerator, I'm gonna do something here, guys. To leave the limit in the numerator, which is, this is not wrong, okay, this is right. But here's the thing. The book decided to invert the signs in here. So this is going to be a minus, this is going to be a plus, this is going to be a minus, and this thing here is also going to be a minus because it wants to leave the limit in the numerator. So you have ln of L minus y minus ln of y. So this thing here is going to be reversed. Okay, it'll be like this. Ln of L minus y divided by y here equals minus kt minus c. So ln minus y divided by y equals e. What e? This e right here, elevated to the minus kt minus c. So it's going to be e to the minus kt times e to the minus c. Okay, now e to the minus c is just a constant. We could call this c, right? But for some reason, the book likes to call this b, e to the minus c. The book likes to call this a b. So you can say that L minus y divided by y equals b e to the minus kt. Okay? Now, let's multiply everything by y. So I'm gonna destroy this thing here. And I'm multiplying everything by y. So you got a y here. Okay, well, I can put a y here times y. That means that what I can do now is to bring this y over. So I'm going to say plus y. I'm going to erase this thing. All right. Now, what do you have in here? You have b times e to the minus kt times y plus y. So I'm going to factor out the y. I'm going to say L equals y. And then you have y divided by y is going to be 1 plus b times e to the minus kt. All right. And then I divide this thing. So I'm going to bring this thing here, a little bit over here, kind of over here. And I'm going to divide this like that, here, here, and get this thing here, put there, there. I'm going to put the equal, oh man. I'm going to put this equals over here. The y, I'll drag it down here. And this is divided. So divided. So there you go. Okay, y is equal to L divided by 1 plus b times e to the minus kt. This is something that you should memorize because you don't want to go through all this stuff all the time. Okay? So whenever you have a growth or decay of a population with respect to time or with respect to anything where there's a limit, this is going to be the derivative. The derivative is going to be like ty dt equals ky times 1 minus y divided by L. This is going to be the format of the rate, right, of the first derivative. And the solution is going to be this. This is the general solution, okay? All right. Now, I'm going to erase everything except here. Here. And just for completeness, I'm going to leave this stuff in here. Okay. It's like a reminder. So let's do an exercise in here. A state game commission releases 4 elk into a game refuge. After 5 years, the elk population is 104. The commission believes that the environment can support no more than 4,000 elk, or elk, I don't know. The growth rate of the elk population P is. The growth rate of the elk population P. So you have the growth rate. Okay, what is it asking for? You have like dp over dt is going to be equal to what? Remember, it's kp. We're doing this. Kp times 1 minus the p, okay, over 4,000, because that's the limit. Okay, write a model for the elk population in terms of t. Well, let's do that. Now we're going to do this. Okay, so p equals the 4,000 divided by 1 plus b times e to the minus kt. This is the solution. Graph the slope for the differential equation, solution that passes through the point 0, 40. I'm not going to graph anything, you guys can do that, but 0, 40. So you see p is going to be 40 when t is equal to 0, so it's going to be 4,000 divided by 1 plus. Guys, when t is equal to 0, this thing here is going to be 1, right? Because it's e to the 0. So this is going to be 1 times b is b. So when you solve for this, right, you're going to do like 40 plus 40b. Okay, hold on. So continuing here, you're going to be 40 plus, because you're multiplying everything by 1 plus b. So 40 plus 40b equals 4,000. So b is going to be equal to 3960 divided by 40. You cut these two. B is going to be equal to 99. So if b is equal to 99, now we can plug that in here. Okay, so this is going to be plus 99. Okay. Use the model to estimate the population elk after 15 years. So after 5 years, the population was 104. Okay, so we can put 104 equals 4,000 divided by 1 plus 99 after 5 years. 99 e to the minus k minus 5k, right? 5k. So what do we do? Well, let's just multiply this thing, right? So it's going to be 104 plus let me see here. 104 times 99, right? Yeah, it's going to be 10,296 e to the minus 5k equals 4,000. Now you bring that over there, okay? Instead of being 4,000, you get that out because minus 104 in here, 4,000 minus 104, which is 3896. I think this is right? Or yeah, minus 104, there you go. So now you do 3896 divided by 10,296. Let's see. 3896 divided by 10,296. Ugh, this is becoming ugly. E to the minus 5k approximates 0.37839. I put 3784. Just going to make an approximation here. Now let's just keep going. We take the ln of everything, okay, and the ln of this is just going to be minus 5k equals the ln of that stuff. So the ln of this is going to be minus 0.971 and an 8. We put a positive here, divide that by 5, make this disappear. K is going to be approximate, right? Because everything here is being approximated. So this stuff divided by 5, I'm going to say divided by 5. So Anyway, yeah. Hey, I got the same answer as the book, approximately 0.194. So if this is approximately 0.194 for k and you have minus to the kt, so you put that in here, okay? Minus 0.194 t. All right, now we have the complete model, right? Estimate the population after 15 years. All you got to do is to replace this t here by 15. You multiply everything, you do all that stuff, and the population is going to be approximately 626. Okay, so when t is equal to 15, p is going to approximate 626. All right. Now, there's something else that's nice. I'm going to erase this thing here because we don't need that anymore. Erase this. Erase this. Okay. Now we have the final model here. And as t increases without bound, because that's what he wants to know. See, find the limit of the model as t goes to infinity. Well, you see, as t goes to infinity, this is going to be p is going to be equal to 4,000 divided by 1 plus 99 divided by e to the 0.194 times infinity. So this is going to be infinity. Okay, this thing here is going to be infinity. E to the infinity equals infinity. 99 divided by the infinity approaches 0. So this is going to approach 0. So this thing is going to approach 4,000 divided by 1 plus 0, which equals 4,000. So you see, as t grows without bounds, for example, what about 1 billion years from now? What about 1 trillion years from now? Hey, the population is going to reach 4,000, which is the limit here. Okay, so that's nice. And guys, on the next video, we're going to see first order linear differential equations, how to solve them.